Welcome back to the Home Lab again, and I've got an interesting little build to show you today. What we're going to look at is a working model of a Lobe pump. Now, you might have already seen my video on counterintuitive meshing gears. That's the clock I made with the square gears that mesh together. But today we're going to look at something that's not dissimilar, the Lobe pump that has these rather unusual interlocking lobes. It's a very interesting and useful pump design, and it has some very specific uses that we're going to talk about in the video. But before we start, just again say a huge thank you to PCBWay for supporting me with this video and encouraging me to make more videos, particularly the ones where I'm building things. If there was ever a video that could have benefited from their CNC machining and 3D printing, this would be it. And as you know, they do bespoke printed circuit boards too. So if you're adding electronics to your project, they're the place to go to. Have a look at their website because there's loads of great ideas there too for projects that you might want to make. Now, I've only become recently aware of Lobe pumps, but they've been around since about the 1860s when the Roots brothers patented a Lobe-based design like this for blowing air into blast furnaces. About 40 or 50 years later, the design was picked up upon and was used for superchargers. So they're the belt-driven devices on high-performance internal combustion engines that are used to blow air into the air intake. And they were very successfully used with cars, even as early as sort of the early 1900s. Anyway, some people refer to those as Roots blowers. So what we're going to do is we're going to have a look at the Lobe pump design. I'm going to show you how I built this one and we'll see if we can get it working. The pump consists of two or more externally gear-driven, contra-rotating meshing cycloidal rotors or lobes that have a very specific shape to them, consisting of two hypercycloid curves that curve inwards and two epicycloid curves that curve outwards around their circumference. I won't even begin to get into the detail of this mathematics in this video, you'll be pleased to hear. Nor did I put a huge effort into getting the shapes correct mathematically at the start of the design, or the build phase, but the end result, I think you'll agree, is quite pleasing. So, to start with, I did some drawings of what my pump should look like. There are pumps with 3 lobes on each rotor, but to keep it simple, I decided to go for a 2-lobe rotor design. Once I played around with this on paper using CAD, or cardboard aided design as Colin Furze calls it, cutting out various lobe shapes and seeing how they fitted together in the case, it was time to get building. Knowing the lobe spacing, I could now order a couple of suitable gears. I was not going to fall into the trap of making the gears myself, as I'd done with the Square Gears clock project and my Leibniz wheel calculator. As ever, for me, Perspex was my go-to material. So, Perspex in hand, it was off to the bandsaw to do some initial cutting, getting the lobes cut from the material removed from cutting out the pump's case. Then, as ever, lots of hole drilling and, as my by-hand cutting was so poor, lots and lots of filing too. At regular intervals, I fitted the parts together to find them binding solid, as my cycloids were far from perfect. But after many trials and more filing, it finally all seemed to work with little or no binding. It's always a great moment, the reveal, when you remove the protective film from your project and fit all of the parts together to see how it's come out. In general, it's not brilliant, and it's only really a demonstration item, but I'm really pleased with how it came out, and I feel just as an artefact it will be quite a talking point. So let's now explain how it's meant to work. Firstly, at the inlet port, as the lobes separate, they initially increase the volume trapped between them and the case, and this creates a partial vacuum, or at least a reduction in pressure, drawing fluid into the pump. Further rotation of the lobes traps the fluid between them and the case, and the fluid is carried around the inner surface of both sides of the casing in the same direction as the lobes are rotating. Once at an outlet, the close mesh of the lobes with each other and the close fit to the case stops fluid returning back to the inlet, as well as the fact that fluid is travelling into the outlet area from both rotors. Further fluid being pumped in forces the fluid in the outlet port of the pump's body and through the outlet pipe. These pumps can even be self-priming. They're often referred to as blowers as they don't compress what enters them. If a gas, they just drive the fluid from the inlet to the outlet port. These pumps have the advantage of being very simple in design and are very efficient. However, their piston-like action results in pulsation of the fluid flow, which can cause vibrations and even cavitation. They're often used in the pharmaceutical and food processing industries as they're easy to sterilise and clean. They can also pump granular solids that are much larger than other types of pump can deal with, as the gaps between the lobes are always quite large. As the lobes do not actually touch each other or the case, they suffer from very little wear too. After a little bit of experimentation and attempts to get it to work, I modified the inlet and outlet ports by widening them so as to make it easier to demonstrate what was going on. It certainly made it easier to pour the fluid glass beads into the pump. So, can we make it work? This worked reasonably well, but the beads are rigid with little give, so they do tend to block and lock the rotors from time to time. I read that Lobe pumps can successfully pump olives, which are rather more flexible than the beads I used. Sorry to disappoint you, but I'm not putting oily olives through my pump by means of an experiment. As I've said before, you get to understand things much better if you make them from scratch, rather than using automatic prototyping methods in the first instance. I hazard a guess that you'd actually go through less iterations, saving more material, if not time, doing it my way, and you'd have a much better working principle of the device you've built. It's a case of make your mistakes early on, and you are talking to the expert here. If I can get it dead wrong first time, I do. I do appreciate that in this case the pump is gravity fed, but the idea is to show you how the fluid, in this case represented by the beads, enters the pump and then is split by the rotors so that it flows around both rotors along the inside of the case. In general though, I hope you agree, this worked reasonably well. Discussion over the dinner table, replete with olives, led me to discuss other options for demonstrating how the pump works, and my partner, not a physicist at all, suggested smoke. So the smoke method was a really good suggestion by my partner. It was quite a fiddly one to set up, but it was fun to do. And one thing that it's really good at showing is the fact that these pumps, if you remember, have a sort of piston action, a sort of pulsing action, which can cause some problems. And you can clearly see that as the smoke goes through the pump. So I do hope you enjoyed this video on the Lobe pump and you got a better understanding of how these devices work. Maybe you can try making one yourself. Do, as ever, please stay to the end of the video because you'll see some other bits that I didn't actually edit in earlier on. And right at the end, I always leave a few links to other videos that I think might interest you. Anyway, I'll be making another video soon, so do please join me then.